Hi ladies and gentlemen, today we're going to do some drawings with shape, polarity, and hybridization. So the first thing that will happen is you're going to be given a compound. In this case we're going to start with one SiCl4. In order to figure out whether or not what the shape is, whether it's polar with a hybridization, the first thing you have to do is you have to draw the Lewis structure. So I'm going to draw my Lewis structure. I'm going to look up silicone. Silicone has 4 valence electrons. Chlorine has 7, and there are 4 of them. So altogether it comes up to 32 valence electrons. I'm going to draw this bad boy out and put Si in the middle. Cl on each side, there's 4 of them. Okay, so now I have this Cl on each side. And I'm going to make sure that Si has an octet. They're all attached. We're cool. What about the chlorines? Alright, 1, 2, 3, 4, 5, 6, 7, 8. Same thing for each one. Okay, and then I'm going to count the dots. And I think this one is a nice, easy, simple one. It is. 8 times 4 is 32. We're good to go here. Here is our Lewis structure. So the first thing we have to deal with is when we are going to figure out the shape, we figure out the number of bonding pairs. So if we look at this little chart that we had in your book, number of bonding pairs on the central atom, in this case silicone, there are 1, 2, 3, 4. And are there any lone pairs? No. So this would be called tetrahedral. That's the shape, tetrahedral. And then hybridization. Hybridization we have talked about a little bit. Hybridization kind of has to do with that same 4 bonding pairs. The way I do it is if there's 4, you have sp, and what number makes that all up to 4? That's 3, sp3. Anything that's tetrahedral will be sp3. It has that 4 bonding pairs that can actually do the bonding. Now, the last thing we're talking about is polarity. If you take a look, polarity is whether or not something is shared evenly or unevenly. If it's polar, it's an uneven share. Take a look at this central atom. Are the electrons equally pulled in all directions? The answer to that is yes. So we call this non-polar. That's the whole molecule is non-polar. It's kind of symmetrical, has the same things on each side. All right, so there's one example. Let's try another one. How about GaH3? Okay, so the first thing we have to draw for GaH3 is we have to draw the Lewis structure. So I'm going to look up Ga. I believe Ga has 3 valence electrons, 3, and hydrogen has 1 times 3, so this is going to equal 6. Now guess what? This one's a kind of a weird exception because it's kind of under boron, and you know that's the exception. So I'm going to draw these H's around here. Kind of go like that with a pair, and we'll just leave that the way it is. There we go, there's the bell. So now gallium's cool, hydrogen's cool, this is the Lewis dot structure. Cool. So what shape is it? We go back to our beautiful trusty chart. How many bonding sites? 1, 2, 3. 3. How many lone pairs? None. So this is trigonal planar. Trigonal planar. Our next problem here becomes hybridization. The way we do hybridization is we take a look at the central atom. How many bonding states? 1, 2, 3. So it's sp2. 1, 2, 3. That's how that works. So sp2. Then let's talk about polarity. Is gallium being pulled equally in each direction? Absolutely. Okay, so that makes it non-polar. Polar means uneven. So since this is even, it is non-polar. All right, let's try another one. Let's maybe try one that might have, I don't know, some lone pairs maybe. Let's try SF6. Okay, this is a big bad boy, so we'll do 6. Okay, that's how many valence electrons a sulfur has, plus 7 times 6. So that comes up to 48. Actually, I think this will work out real nice. S, and we're going to put 6 fluorines around it, so I'm going to try and do this. Oh man, that's an expanded octet. Alright, so already sulfur has these 2, 4, 6, 8, 10, 12 electrons around it, but let's make sure each one of the fluorines has what it needs. I believe if it does, then we're looking at 48. And no lone pairs. All right, so that's 1, 2, yep, that's 48 dots. Sweet, cool. So now we have our 48 dots. Now it's time to take a look at what's the shape. Well, how many bonding sites? 6. Are there any lone pairs? No, so it's octahedral. And there are 6 bonding places, so that would be S, P. Well, 3 is the maximum you can have in P, but that's 1, 2, 3, 4, so it's D2. That would be the hybridization for this substance. Now we also have to figure out, is it polar or nonpolar? Is everything being pulled equally here? All the same electronegativities in fluorine, so this would be considered nonpolar. All right, let's try another. And then maybe that'll be enough for now. Let's try SO2, okay? How many valence electrons does sulfur have? 6. Oxygen is 6 times 2, so that comes up to 18 valence electrons. Put sulfur in the middle, put oxygen on both sides. We're going to make sure everybody has 8. And when I count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 20, oh man, that can't work. So it must mean since we have more, we're not going to expand, we're instead going to make a double bond. So I'm going to take and make this a double bond. This oxygen right here, and make sure that has 8. And right here, the sulfur needs another 2. Cool, all right. So here's the deal, 2, 4, 6, 8, 10, 12, 14, 16, 18. 18, we are good to go. This is absolutely right. We're going to talk about something here in a minute called resonance, but we're going to deal with that. We're going to deal with shape and all that first. So now, if we look here for shape, how many bonding sites are there on the sulfur? 1, 2, 3. Okay, that one that isn't bonded is still a site that can be used. So we're going to go to 3. How many lone pairs? There's 1. So according to our chart, that would make this bent. The shape is bent. Now, how many bonding sites are there? Well, there are 3. That didn't change. So it's sp2. 1, 2, 3. Okay, so we have that as our hybridization. Now, polarity, okay, if we take a look at polarity here, okay, is there an equal pull on each side? Well, there is equal oxygen, and the fact that this is a double bond versus single bond doesn't matter in this case. But look at this lone pair. That causes an uneven pull. So because of that uneven pull, this is going to be considered a polar substance. All right. Now, I said the word resonance a minute ago. Resonance means that electrons don't just stay in the same place, especially if there's a place for them to move. So in addition to this formula, you can also write it in another way. And I'm going to draw this little arrow that goes back and forth because they go between these 2 structures. I'm going to draw just the same thing except for backwards. So instead of the double bond being on the first oxygen, the double bond is on the last oxygen. That way, the electrons kind of move from place to place, and it shows that that can happen. And that, ladies and gentlemen, is called resonance. All right, so for now, that's kind of a quick overview of how to do Lewis structures with VSEPR and polarity quickly. Hope you had a great day. Talk to you later.